The morning of February 17th, 1944, a concrete bunker 17 kilometers northeast of Rome, where Major Kurt Hoffmann of the Luftwaffe's Technical Intelligence Section stood over a workbench, staring at components that should not exist. The device before him had been recovered 2 days earlier from the Anzio beachhead, pulled from a bombed-out American anti-aircraft battery before Allied forces could destroy it. Standard procedure dictated immediate analysis of captured equipment. What Hoffmann found in his initial examination made him request an emergency meeting with his superiors. The Americans had deployed something new, something the German technical intelligence apparatus had completely failed to anticipate, and German pilots were dying because of it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The equipment carried American military designation SCR-584, a name that meant nothing to Hoffmann when he first saw it stenciled on the trailer housing. What mattered was what the system could do, capabilities that violated every assumption German radar engineers had made about the limits of fire control technology. Hoffmann had spent the previous 18 hours conducting preliminary tests on the undamaged components, cross-referencing his findings with Luftwaffe loss reports from the Anzio operation. The correlation he discovered was precise, mathematical, and catastrophic. Every anomalous aircraft loss, every inexplicable anti-aircraft hit, every instance where German fighters had been shot down by ground fire that seemed impossibly accurate, all of it traced back to this radar system. The Americans had not just improved their anti-aircraft capabilities. They had achieved something close to perfection. Hoffmann's background made him uniquely qualified to understand what he was examining and uniquely disturbed by its implications. He'd trained as an electrical engineer at the Technical University of Berlin before joining the Luftwaffe in 1938, specializing in radar, technology development and analysis. He'd worked on the Würzburg gun-laying radar project, understood its capabilities and limitations intimately, and had reviewed captured British and American radar equipment throughout the war. Nothing in his experience had prepared him for what sat disassembled on his workbench. The technical sophistication represented a leap forward that German radar engineers had considered theoretically possible but practically unachievable given wartime constraints. Yet here it was, mass-produced and deployed in quantity, making Luftwaffe attacks over the Anzio beachhead a mathematical death sentence. The Anzio landings had begun on January 22, 1944, with Operation Shingle placing 50,000 Allied troops behind German defensive lines. Initial Luftwaffe response had been aggressive. German commanders viewed the isolated beachhead as an opportunity, a chance to inflict serious damage on concentrated Allied forces before they could break out toward Rome. The Luftwaffe committed substantial resources to attacking the beachhead, flying hundreds of sorties against shipping and ground positions during the first week of operations. German pilots reported heavy anti-aircraft fire, which was expected over any major military target. What they couldn't explain was the accuracy. Anti-aircraft fire had always been a statistical problem, solved through volume. You put enough shells in the sky, and some percentage would find their targets through probability rather than precision. Allied anti-aircraft defences at Anzio operated under different rules. German bomber crews described anti-aircraft shells that seemed to track their aircraft, that followed evasive manoeuvres with unnatural consistency. Fighter pilots reported getting locked by ground fire before they reached effective attack altitude, shells bursting precisely at their flight level with accuracy that suggested optical fire control, except the attacks came at night, in clouds, through weather conditions where optical targeting was impossible. Luftwaffe intelligence officers initially attributed these reports to combat stress and exaggeration. Pilots always overestimated enemy capabilities under fire, but the loss statistics told an unambiguous story. During the first week of operations, Luftwaffe aircraft were being shot down at double the expected rate. By the second week, loss rates had tripled. Something at Anzio was killing German aircraft with efficiency that exceeded anything the Luftwaffe had encountered in the Mediterranean theatre. The anomaly became statistically undeniable by early February. The Luftwaffe launched a major attack on February 3rd, sending nearly 70 aircraft against Allied shipping in the beachhead. Anti-aircraft fire destroyed or damaged 40% of the attacking force. Standard doctrine suggested maximum loss rates of 12 to 15% during heavy anti-aircraft engagement. 40% exceeded every historical benchmark. Either Allied anti-aircraft gunners at Anzio had achieved supernatural marksmanship, or they possessed technology that fundamentally altered the mathematics of aerial combat. German commanders needed to understand which. If it was technology, they needed to capture it, analyze it, and develop countermeasures before it spread beyond the isolated battlefield at Anzio. The opportunity came during a German counterattack on February 16, when advance elements of the 14th Army overran a section of the Allied defensive line. Among the positions captured was a trailer-mounted radar installation that American forces had attempted to demolish but failed to completely destroy. German combat engineers extracted what remained of the equipment and transported it to the nearest technical intelligence facility, where it landed on Hoffmann's workbench less than 24 hours after capture. He'd examined captured Allied equipment before, studied British radar systems seized in North Africa, analyzed American SCR-584 units recovered from Sicily. The SCR-584 represented something categorically different. Where the SCR-268 had been an incremental improvement over existing German systems, comparable to the Würzburg in capability and design philosophy, the SCR-584 operated on principles that German engineers had discussed in theoretical papers but never implemented in operational hardware. The wavelength was the first shock. German fire control radars, including the Würzburg, operated at wavelengths around 53 to 54 centimeters, in the high UHF band. The SCR-584 operated at approximately 10 centimeters, in the microwave S-band. That five-fold reduction in wavelength translated directly into improved resolution, tighter beam focus, and more precise target tracking. German radar engineers understood the advantages of shorter wavelengths. They'd been trying to develop operational microwave systems for years. The technical challenges were immense. Generating sufficient power at microwave frequencies required components that German industry struggled to manufacture reliably. The magnetron tubes needed for microwave transmission demanded manufacturing precision beyond what German factories could consistently achieve under wartime conditions. Raw material shortages, particularly in rare metals needed for vacuum tube production, constrained development further. Allied strategic bombing had degraded German electronics manufacturing capacity throughout 1943, making advanced development work increasingly difficult. Yet the Americans had solved all of these problems and deployed the result in quantity. Hoffmann estimated from the serial numbers visible on various components that hundreds of SCR-584 units had been manufactured. This wasn't a prototype or limited trial system. It was standard equipment, mass-produced, field-deployed, and obviously working with devastating effectiveness. The implications extended beyond radar engineering. If American industry could mass-produce microwave radar systems while simultaneously supporting global military operations, their industrial capacity exceeded German intelligence estimates by margins that made previous assessments laughably inadequate. Hoffmann focused on documenting technical specifications. Strategic implications were above his authority. His job was to determine what the system could do, how it worked, and whether German forces could counter it. The preliminary answers were precise, comprehensive, and deeply troubling. The SCR-584 incorporated automatic tracking, driven by servo motors that kept the radar dish locked on target without manual operator intervention. German Würzburg radars required skilled operators to manually track targets using visual displays and hand controls. The process demanded constant attention and significant training. Even experienced operators struggled to maintain lock on maneuvering targets, especially at high speeds or during violent evasive action. The American system removed human limitations from the tracking process. Once locked onto a target, the radar followed automatically, compensating for evasive maneuvers faster than any human operator could react. The servo system responded to signal variations in milliseconds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this, adjusting antenna position continuously to maintain maximum signal strength. Target aircraft could turn, climb, dive, or attempt any evasive maneuver. The radar stayed locked. Breaking lock required either destroying the system or escaping beyond its effective range. Neither option was practical for aircraft already engaged by accurate anti-aircraft fire. The system integrated with an analog computer, designated the M9 director. Hoffmann had recovered fragments of documentation describing the integration. The M9 received tracking data from the radar, calculated continuous solutions for gun laying, and transmitted firing commands directly to 4 90mm anti-aircraft guns positioned around the radar installation. The entire system operated as an integrated unit. Radar acquired and tracked the target. The computer calculated trajectory. The guns fired automatically. Human operators supervised but did not control the engagement. The loop from detection to firing operated faster than human reaction time allowed, with precision that exceeded manual methods by orders of magnitude. German anti-aircraft doctrine relied on predicted firing, where operators estimated where an aircraft would be when shells reached target altitude, then fired into that predicted space. The American system calculated continuous solutions, updating predictions multiple times per second based on actual aircraft movement. It didn't predict where the target might go. It followed where the target actually went and adjusted gun solutions in real time. Hoffmann cross-referenced his technical analysis with Luftwaffe loss reports. The correlation was mathematically precise. Aircraft shot down over Anzio displayed damage patterns consistent with direct hits rather than proximity explosions. Shells weren't bursting near aircraft. They were striking aircraft, punching through wings, fuselages, and engines with accuracy that suggested optical fire control. Except the hits came through clouds. At night, in conditions where optical targeting was impossible, the SCR-584 was delivering visual accuracy targeting through electronic means, maintaining lock through weather and darkness that blinded traditional methods. German pilots reported that evasive maneuvers seemed ineffective over Anzio. Now Hoffmann understood why. The radar tracked faster than aircraft could maneuver. Every turn, every altitude change, every attempt to break lock simply gave the tracking system new data to process. The M9 computer incorporated those changes into updated firing solutions within fractions of a second. By the time a pilot completed an evasive maneuver, the guns were already firing at his new position. The technical briefing Hoffmann prepared for his superiors documented capabilities that seemed almost impossible. Detection range extended to 64 kilometers for large aircraft. Tracking mode could maintain lock at ranges exceeding 30 kilometers. Accuracy in tracking mode approached 23 meters in range and 0.2 degrees in azimuth and elevation. Those specifications exceeded the Würzburg Riese, Germany's largest and most capable gun-laying radar, which had been designed specifically to match British bombing altitudes. The Americans had exceeded German best-effort engineering with a trailer-mounted mobile system that could be deployed rapidly and operated by relatively untrained crews. The automation meant American anti-aircraft batteries didn't require the months of training German batteries needed to achieve comparable accuracy. The radar did most of the work. Operators mainly monitored system status and selected targets. A German flak battery needed experienced crews, extensive practice, and ideal conditions to achieve kill rates of 10 to 12%. An SCR-584 equipped American battery operated by average crews under poor conditions could achieve kill rates exceeding 30%. That threefold advantage in effectiveness translated directly into aircraft losses the Luftwaffe could not sustain. Hoffmann's report reached Luftwaffe High Command on February 19, where it generated responses ranging from skepticism to alarm. General Joseph Kammhuber, who commanded German night fighter operations and understood radar technology intimately, recognized immediately what the SCR-584 represented. He'd spent years building Germany's air defense network, integrating Freya early warning radars with Würzburg gun-laying systems to create the defensive line that bore his name. He understood the limitations of existing technology. the compromises required to make systems work under operational conditions, and the theoretical improvements that remained frustratingly out of reach. The SCR-584 had achieved those improvements. Kamhuber requested immediate analysis of whether similar systems had been deployed elsewhere, particularly over Britain, where German bombing operations continued intermittently and where American heavy bomber formations staged before attacking German industrial targets. Intelligence officers compiled reports from multiple theaters. The pattern emerged quickly and was universally bad. SCR-584 radars had been deployed in England starting in mid-1943, initially in small numbers as field testing units, then in increasing quantity throughout the fall. By December, British anti-aircraft defences around high-value targets incorporated the American radar as standard equipment. The V-1 flying bomb campaign, which was supposed to overwhelm British defences through sheer numbers of fast-moving targets, had been expected to achieve hit rates of 60 to 70% based on pre-deployment calculations. Actual hit rates fell below 30%, with the shortfall attributed primarily to unexpectedly effective anti-aircraft fire. The SCR-584, integrated with proximity-fused shells, could track and destroy Vohn's second with efficiency that made the entire weapon system economically unviable. Germany was expending enormous resources, building flying bombs that British defences destroyed before they reached their targets. The radar had also been deployed in the Pacific theatre, though reports from that region were fragmentary. What little intelligence reached Germany suggested American anti-aircraft defences in the Philippines and New Guinea had achieved similar dramatic improvements in effectiveness. The pattern was clear. This wasn't a local deployment at Anzio. It was a systemic upgrade of Allied anti-aircraft capabilities across all theatres, implemented rapidly and at a scale that suggested enormous manufacturing capacity. German intelligence estimated American production of SCR-584 units at approximately 1,500 systems annually, possibly higher. For context, total German production of Würzburg radars across all variants averaged around 400 units annually at peak output, and that production was declining under Allied bombing pressure. The Americans were outproducing Germany by nearly 4-to-1 in advanced radar systems alone, while simultaneously manufacturing vastly larger quantities of aircraft, vehicles, ammunition, and every other category of military equipment. Oberst Werner Baumbach, who commanded Luftwaffe bomber operations in Italy, absorbed Hoffmann's report with the grim recognition of someone who'd been losing aircraft to an enemy he didn't understand and now understood too well. He'd been flying combat missions since 1939, survived the Battle of Britain, commanded units on the Eastern Front, and accumulated enough operational experience to distinguish between tactical setbacks and fundamental problems. The SCR-584 represented a fundamental problem. German aircraft attacking targets defended by these radars faced mathematical death. Not risk, not danger, mathematical certainty that sustained operations would produce unsustainable losses. Baumbach had access to detailed loss statistics from the Anzio operations. During 3 weeks of sustained attacks, the Luftwaffe had committed approximately 450 aircraft sorties against the beachhead. 96 aircraft had been destroyed or damaged beyond repair. 117 aircrew were dead or missing. Loss rates of 21% per sortie exceeded every sustainable operational threshold. Standard Luftwaffe doctrine considered loss rates above 12% operationally prohibitive. You couldn't maintain force strength, train replacements fast enough, or sustain crew morale when 1 in 5 aircraft failed to return. 21% losses meant force destruction within weeks. Either you stopped attacking, or you accepted complete attrition of your attacking units. Neither option was acceptable. Stopping attacks meant yielding initiative completely to the Allies, allowing them to build up forces and break out from the beachhead without air harassment. Continuing attacks meant destroying your own air force for diminishing returns. Baumbach looked for tactical solutions. Perhaps attacking at different altitudes would reduce vulnerability. Analysis showed the SCR-584's tracking accuracy remained effective from near ground level to above 30,000 feet. Perhaps attacking from different angles would exploit radar dead zones. The system's conical scanning eliminated traditional dead zones. Perhaps saturating defenses with mass formations would overwhelm tracking capacity. Each SCR-584 could guide 4 guns simultaneously, and Allied positions mounted multiple radar installations. Saturation attacks just meant more aircraft flying into more accurate fire. Perhaps attacking at night would reduce effectiveness. The radar operated identically in darkness and daylight. Weather that grounded optical observation didn't affect microwave tracking. The only tactical advantage was distance, attack from beyond the radar's range. But effective attack range for German bombers was shorter than the SCR-584's detection range, and closing to weapons release meant entering the engagement envelope where the system's accuracy was absolute. Every tactical option Baumbach examined led to the same conclusion. There was no tactical solution. The technology itself was the problem. Until Germany developed comparable systems or effective countermeasures, any aircraft operating in defended airspace faced vastly increased risk, and time required for German development meant years, not months. The Americans would continue deploying these systems across all theaters, while German engineers struggled to replicate capabilities that American industry was mass-producing. The strategic implications reached beyond immediate tactical concerns. Reichsmarschall Hermann Göring, commander of the Luftwaffe, received briefings on the SCR-584 inches early March. His response combined technical denial with political deflection. The system couldn't be as effective as reports suggested. American propaganda exaggerated capabilities. German radar development would produce comparable systems shortly. The losses at Anzio resulted from tactical errors and poor leadership, not from insurmountable technical superiority. This response pattern was familiar to officers who'd briefed Göring on previous technological setbacks. He'd dismissed reports of British radar effectiveness before the Battle of Britain, rejected intelligence assessments of Soviet tank production capacity in 1941, and consistently underestimated Allied industrial capabilities throughout the war. His reaction to the SCR-584 followed the same template. Acknowledge the problem minimally, blame subordinates for failures, promise imminent German solutions, and change no fundamental policies. The engineers at Telefunken and other German radar manufacturers received urgent requests to develop countermeasures and equivalent systems. Their responses were technically detailed and strategically useless. Countermeasures to the SCR-584's conical scanning system were theoretically possible, but required development time measured in months, assuming resources and materials that were increasingly unavailable. Manufacturing comparable microwave radar systems would require entirely new production facilities, specialized components that German industry couldn't produce in quantity, and fundamental reorganization of radar development priorities. Even if everything went perfectly, operational deployment wouldn't begin until late 1945 at the earliest. By then, the war's outcome would already be determined by factors well beyond radar technology. The engineers couldn't say this explicitly in official reports, so they buried the reality in technical language about development timelines, resource requirements, and production constraints. Major Hoffmann continued analyzing the captured SCR-584 components throughout February and March, documenting every design detail he could extract from the damaged equipment. His reports became increasingly technical and increasingly pessimistic. The American system incorporated engineering solutions that German designers had considered but rejected as too expensive, too complex, or too demanding of manufacturing precision. The Americans had implemented all of those expensive, complex, precision-demanding solutions and made them work reliably in field conditions. The modular design allowed rapid maintenance and field repair. Failed components could be swapped in minutes rather than hours. The automatic calibration systems reduced setup time from hours to minutes. The power supply systems operated reliably under field conditions that would disable more delicate German equipment. Every aspect of the design reflected an engineering philosophy that prioritized operational effectiveness over manufacturing efficiency, that accepted higher production costs to achieve superior field performance. German radar development operated under opposite constraints. Manufacturing efficiency was paramount because Germany lacked the industrial capacity to produce unlimited quantities of expensive systems. Designs prioritized simplicity over capability, manual operation over automation, and minimal use of scarce materials over optimal performance. These weren't bad engineering decisions given German constraints. They were rational responses to limited resources. But rational design choices based on limited resources produced systems that couldn't compete with designs built without resource constraints. The SCR-584 existed because American industry could manufacture precision magnetrons in quantity, could produce high-quality vacuum tubes reliably, could source the specialized metals and materials needed for microwave components, and could design for optimal performance without constantly compromising for material shortages. German engineers operated in an environment where every design choice was a compromise between what worked best and what could actually be built, given available resources. Hoffmann's most significant finding came in late March, when he successfully powered up portions of the captured radar using improvised German components. The system operated exactly as American documentation described, with performance specifications that matched or exceeded the manufacturer's claims. This was significant because German radar systems typically performed worse in field conditions than in controlled testing. The Americans had built a system whose field performance matched its design specifications, suggesting manufacturing quality control and engineering discipline that German industry struggled to match. The difference wasn't theoretical knowledge. German engineers understood the physics as well as their American counterparts. The difference was implementation. American industry could build what engineers designed, reliably, repeatedly, in quantity. German industry increasingly could not. This manufacturing superiority extended across all categories of military equipment. Intelligence assessments compiled throughout spring 1944 painted a comprehensive picture of Allied industrial advantages. American aircraft production exceeded German output by ratios exceeding 3-to-1. American shipbuilding replaced losses faster than German submarines could sink vessels. American ammunition production supplied multiple Allied armies simultaneously, while German forces rationed shells. American fuel production provided unlimited aviation gasoline, while the Luftwaffe increasingly grounded aircraft for lack of fuel. The SCR-584 was just one visible example of a systemic industrial advantage that touched every aspect of the war. Germany was fighting enemies who could produce more weapons, train more troops, replace more losses, and develop better technology faster than German industry could respond. The mathematics of industrial attrition made German victory increasingly implausible. Luftwaffe tactical doctrine evolved throughout spring and summer of 1944 to account for the new reality. Attack patterns shifted to minimize exposure to radar-directed fire. Units avoided areas where SCR-584 deployment was confirmed. Attack altitudes changed to exploit marginal performance variations. None of these adaptations solved the fundamental problem. They just reduced losses from catastrophic to merely unsustainable. The Luftwaffe's monthly loss rates climbed steadily from January through June as Allied forces advanced and deployed more radar-equipped anti-aircraft batteries. Aircraft destroyed exceeded replacement production. Experienced aircrew losses exceeded training pipeline output. The force was consuming itself faster than it could regenerate. By June, when Allied forces invaded Normandy, the Luftwaffe could barely contest the invasion beaches. Not because German pilots lacked courage or skill, but because the force had been systematically destroyed over preceding months in a war of attrition where German losses exceeded replacement capacity while Allied forces grew stronger. The Normandy invasion demonstrated the SCR-584's effectiveness at operational scale. Allied anti-aircraft defenses shot down 70% of German aircraft that attempted attacks on the invasion beaches during the first week. 70%. The Luftwaffe essentially ceased to exist as an effective force in the West within days. Those aircraft and crews represented years of training, enormous resource investment, and irreplaceable combat experience. They flew into radar-directed fire that destroyed them with efficiency that made their sacrifice strategically meaningless. German commanders watched their air force evaporate, and could do nothing to prevent it. The tactical situation was hopeless. Continue attacking and lose everything quickly, or stop attacking and lose initiative completely. Either choice led to defeat. The only variable was timeline. The broader realization emerged gradually through summer 1944, documented in intelligence assessments and command discussions that grew increasingly pessimistic. The SCR-584 represented a small but perfect example of why Germany would lose the war. American industrial capacity could identify problems, develop solutions, manufacture those solutions in quantity, and deploy them effectively across global battlefields while simultaneously supporting multiple Allied nations. German industry struggled to maintain existing production levels under bombing pressure, couldn't develop equivalent solutions quickly enough to matter, and operated under resource constraints that forced constant compromises between capability and manufacturing feasibility. This industrial disparity existed across every category of military technology. Radar was just the category where the gap was most visible and most immediately lethal. By August 1944, Major Hoffmann had completed his comprehensive technical assessment of the SCR-584. His final report ran to 147 pages of detailed engineering analysis, operational assessments, and strategic implications. The conclusions section was brief, precise, and devastating. Germany possessed neither the industrial capacity nor the technical resources to develop equivalent systems within timeframes that would affect the war's outcome. Existing countermeasures were marginally effective at best and required resources Germany couldn't spare. The Americans would continue deploying these systems in increasing numbers across all theaters. Luftwaffe loss rates would continue climbing. No tactical adjustments could compensate for the fundamental technological advantage the radar represented. The report recommended immediate cessation of daylight attacks on heavily defended targets, significant reduction in offensive operations over areas with confirmed SCR-584 deployment, and reallocation of remaining air resources to defensive operations, where German radar systems provided some advantage. These recommendations were strategically sound and politically impossible. Implementing them meant abandoning offensive air operations entirely, ceding air superiority completely to the Allies, and accepting that the Luftwaffe's role would be limited to desperately defending German airspace against overwhelming Allied bombing campaigns. Hoffmann's report circulated through Luftwaffe command channels, accumulating endorsements from technical experts and operational commanders who recognized its accuracy, and rejection from leadership who couldn't accept its implications. The report disappeared into classified files, where it joined hundreds of other assessments documenting various dimensions of Germany's deteriorating position. The truth it contained was mathematically undeniable and strategically irrelevant. German leadership wasn't making decisions based on accurate assessment of capabilities and outcomes. They were making decisions based on ideology, political imperatives, and Hitler's refusal to acknowledge that Germany could lose. Accurate intelligence became worthless when leadership rejected any conclusions inconsistent with predetermined beliefs about German superiority and inevitable victory. The human cost of this denial accumulated throughout the war's final year. German pilots continued flying missions against targets they couldn't effectively attack, losing aircraft and lives to defenses they couldn't overcome, achieving tactical results too marginal to affect strategic outcomes. Every sortie against Allied positions defended by SCR-584 radars was essentially a suicide, mission dressed in operational orders. The pilots knew this. Their commanders knew this. But the missions continued because stopping meant admitting the war was lost, and that admission remained politically impossible until Germany's complete military collapse made it undeniable. Lieutenant Franz Stigler, a Luftwaffe fighter pilot who survived the war and later emigrated to Canada, described in post-war interviews the psychological impact of facing radar-directed anti-aircraft fire. He'd flown combat missions since 1940, survived the Battle of Britain, fought over North Africa and the Eastern Front, and accumulated enough experience to distinguish between normal combat danger and mathematically certain death. Attacking targets defended by the American radar systems felt like flying into a machine designed specifically to kill aircraft, he recalled. The shells didn't just fill the sky randomly, they found you. You could see them tracking, following your maneuvers, adjusting to match your evasive actions. Other pilots described similar experiences, the sense of being hunted by something that never missed, that responded faster than human reflexes allowed, that maintained accuracy through conditions where human gunners would be blind. The psychological effect was cumulative and devastating. Pilots who'd maintained morale through years of combat broke when faced with defenses that seemed unbeatable. Units that had sustained operational effectiveness, despite heavy losses, disintegrated when loss rates climbed beyond the point where survival seemed possible. The Luftwaffe's collapse in the war's final year resulted partly from material shortages and numerical inferiority, but also from the psychological destruction of crews who understood they were being sent to die for no achievable purpose. The SCR-584's deployment accelerated through fall 1944 and into 1945. Allied forces advancing through France and into Germany brought mobile radar installations with them, creating expanding zones where German air operations became effectively impossible. The defense of the Reich, Germany's last-ditch effort to protect industrial centers and population from Allied bombing, faced American bomber formations escorted by long-range fighters and protected by radar systems that made German fighter attacks catastrophically expensive. In January 1945, the Luftwaffe lost 43% of its remaining fighter strength in a single month, mostly to combat losses that couldn't be replaced. By March, the force barely existed in operational terms. Aircraft sat grounded for lack of fuel. Trained pilots were scarce. Replacement aircraft arrived in numbers insufficient to compensate for losses. The organization that had dominated European skies in 1940 had been systematically destroyed through attrition warfare, where German losses exceeded sustainable rates, while Allied forces grew stronger. The final months of the war saw desperate German attempts to deploy technological solutions that might restore some balance. The Me-262 jet fighter offered performance advantages that should have posed serious problems for Allied bombers. But jets were too few, introduced too late, and operated by undertrained pilots flying from airfields under constant attack. The NATO rocket interceptor represented even more extreme desperation. A manned missile launched vertically to attack bomber formations, piloted by undertrained volunteers with minimal flight experience. These weapons weren't solutions. They were symptoms of systemic collapse, evidence that German leadership had lost touch with reality so completely that they committed resources to programs with no chance of affecting outcomes. The SCR-584 continued operating with boring reliability throughout this period. The system wasn't dramatic or newsworthy. It just worked, day after day, shooting down aircraft with mechanical precision, protecting Allied forces with effectiveness that made German air attacks economically futile. Post-war analysis by Allied intelligence services documented the SCR-584's combat effectiveness across all theaters. The system had been deployed in approximately 1,700 installations by war's end, protecting ships, air bases, supply depots, and advancing ground forces. Kill rates against attacking aircraft averaged between 30% and 40% in most engagements, more than triple the effectiveness of previous anti-aircraft systems. In some specific operations, particularly against V-1 flying bombs, kill rates exceeded 70%. The economic efficiency was striking. Each SCR-584 installation cost approximately $200,000 to manufacture and deploy. Each German aircraft destroyed represented hundreds of thousands of dollars in production costs, thousands of hours of pilot training, and irreplaceable combat experience. The return on investment was exceptional. Allied industrial capacity could produce radar systems faster than Germany could produce aircraft to be destroyed by those systems. German technical intelligence services interviewed after the war confirmed what Hoffmann's original assessment had documented. The SCR-584 represented a technological advantage that Germany couldn't counter within operationally relevant timeframes. German radar engineers understood the principles. They'd been working on similar concepts since before the war, but understanding principles wasn't enough. Implementation required manufacturing capabilities that Germany lacked, resources Germany couldn't secure, and development time Germany didn't have. The gap between theoretical knowledge and practical implementation was where wars were won and lost. Germany had the knowledge. The Allies had the implementation capacity. That difference was decisive. The broader lesson transcended radar technology specifically. Modern industrial warfare rewarded manufacturing capacity more than tactical brilliance, production efficiency more than individual courage, and systematic resource advantage more than operational creativity. Germany's military had excelled at tactics, demonstrated exceptional operational flexibility, and fielded some of the war's most capable individual weapons systems. None of that mattered when facing enemies who could produce more weapons, replace more losses, develop better technology faster, and sustain operations at scales Germany couldn't match. The SCR-584 was a perfect microcosm of this reality. German engineers knew such systems were theoretically possible. American engineers built them, mass-produced them, and deployed them effectively across global battlefields. That difference between knowing and doing was the difference between losing and winning. Major Hoffmann survived the war and worked in German electronics industry during the post-war reconstruction. He maintained detailed technical documentation from his wartime radar analysis, including his comprehensive SCR-584 assessment. In interviews conducted during the 1970s, he reflected on the significance of that February morning when he'd first examined the captured American radar. "We understood immediately that we were looking at equipment we couldn't match," he said, "not because we lacked knowledge or skill, but because we lacked the industrial capacity to build what we knew how to design." That was the real revelation. The Americans weren't just ahead in specific technologies. They had the manufacturing base to implement advanced designs at scale, while we struggled to maintain production of existing systems. The radar was just one example, but it was a perfect example of why we lost. They could build more, build better, and build faster than we could destroy. Once that gap opened, no amount of tactical skill could close it. His assessment remained accurate decades after the war's end. The SCR-584 represented a specific technological achievement, but its significance lay in what it demonstrated about comparative industrial capabilities. By 1944, Allied industrial production exceeded German capacity by margins that made military victory mathematically determined. The radar didn't cause German defeat. It was evidence of the industrial realities that made defeat inevitable. The system's technical legacy extended well beyond World War II. SCR-584 radars remained in service with various militaries into the 1950s, adapted for new roles as air defense requirements evolved. The basic principles, automatic tracking, microwave frequencies, integrated fire control, became standard in radar development worldwide. Soviet engineers studied captured SCR-584 units and developed derivative systems, including the SON-9, SON-30, and SON-50 radars used in subsequent conflicts. The technical espionage conducted by Morton Sobel, who stole SCR-584 plans and provided them to the Soviet Union, represented one of the Cold War's significant intelligence breaches. The technology that helped destroy the Luftwaffe later contributed to air defense systems that American aircraft would face in Korea and Vietnam. Technologies developed for one war became weapons in subsequent conflicts, spreading through military establishments worldwide as nations studied and copied successful systems. MIT's radiation laboratory, which developed the SCR-584, became the foundation for subsequent radar development efforts, including the establishment of MIT Lincoln Laboratory. The engineering talent assembled to create wartime radar systems transitioned into Cold War defense research, developing increasingly sophisticated systems for detecting and tracking aircraft, missiles, and eventually spacecraft. The SCR-584 represented an early achievement in a continuous line of development that extended through decades of technological advancement. The modular design philosophy, integrated systems approach, and focus on operational reliability over manufacturing simplicity influenced electronics engineering well beyond military applications. Commercial radar systems, air traffic control, and numerous civilian applications inherited principles developed for the SCR-584 and similar wartime systems. For the Luftwaffe pilots who faced radar-directed anti-aircraft fire during 1944 and 45, the technical legacy was irrelevant. What mattered was the immediate reality of flying into defenses that killed with mechanical precision. Those who survived carried memories of watching squadron mates destroyed by fire that seemed impossibly accurate, of understanding that continued operations meant mathematical death, of recognizing that courage and skill couldn't compensate for technological inferiority. The psychological burden of fighting unwinnable battles under orders from leadership that refused to acknowledge reality created trauma that persisted long after the war ended. Victory required more than bravery. It required resources, industrial capacity, technological advantage, and realistic assessment of capabilities versus opposition. Germany lacked all of these by 1944. The SCR-584 was just the specific piece of equipment that made the disparity visible in a way that couldn't be ignored or explained away. The story of German commanders studying captured American radar equipment represented a moment of clarity in a war characterized by delusion and denial. For a brief period, technical experts confronted undeniable evidence that Germany faced enemies with overwhelming industrial advantages. The reports they wrote documented this reality precisely and professionally. Their leadership ignored those reports and continued policies that guaranteed defeat while maximizing casualties and destruction. The tragedy wasn't that Germany lost. The tragedy was that the loss was predictable, documented, and presented to leadership who rejected mathematical reality in favor of ideological fantasy. Millions died in fighting that professional analysis showed couldn't change outcomes. Cities were destroyed, populations were devastated, Europe was shattered, and throughout it all, intelligence reports sat in files documenting the certainty of defeat, read by commanders who understood the truth but lacked authority to act on it, and ignored by leaders who preferred comfortable lies to uncomfortable facts. The SCR-584 sits today in museums, including MIT Lincoln Laboratory's commemorative display. Visitors can examine the dish antenna, the control systems, the vacuum tubes, and components that represented cutting-edge technology 8 decades ago. The exhibits explain the radar's role in defeating V-1 flying bombs, protecting Allied forces, and contributing to air superiority that enabled invasion and ultimate victory. What the exhibits can't fully convey is what it meant to be a German pilot in 1944, watching the radar's dish track your aircraft, knowing that guns were being automatically laid onto your position, understanding that evasive maneuvers wouldn't help, recognizing that you were flying into a killing machine that represented industrial capabilities your nation couldn't match. That psychological reality existed in the moment, experienced by men who mostly didn't survive to describe it, lost in the statistical aggregation of loss rates and casualty reports. The captured radar that Major Hoffmann examined in February 1944 represented a small piece of equipment with enormous implications. It documented American technical achievement. It demonstrated industrial capabilities Germany couldn't match. It proved that knowledge without implementation capacity was strategically worthless. And it provided concrete, undeniable evidence that Germany was losing a war it couldn't win against enemies with overwhelming material advantages. German commanders studied the captured SCR-584 radar and understood why. Messerschmitts were dying. They were dying because American industry could build systems German industry couldn't match, deploy them faster than German forces could adapt, and manufacture them in quantities that made German countermeasures irrelevant. That understanding came too late to matter, buried in classified reports filed by engineers whose expertise was valued but whose conclusions were ignored. The radar continued operating with mechanical precision, tracking targets, directing fire, destroying aircraft, and demonstrating through accumulated kills the mathematical certainty of German defeat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.